Okay, everybody, welcome to the MAE Senior Design Engine Project Conference. So this is our second presentation. The first presentation was closed to the public. Our presenter are Thomas Miles, Lee Harris, Alan Lubers, and Kyle Michel. Their project title is Aerodynamic and Validation Package for Formula SAE Vehicles. So the faculty advisors are William Liu and Dr. Marathi. So welcome everybody. So the presentation will be for 20 minutes. And after the presentation, we will have question and answer session for 5 minutes. And that will conclude this 9:30 a.m. as a presentation. The next presentation will be at 10 a.m. Okay, welcome everybody again on the behalf of Mechanical and Aerospace Department, College of Applied Science, Engineering of Applied Science, WMU. The presenter is your floor now.
All right, thank you, Dr. Shrestha. Welcome everyone again. My name is Alan Juarez. Thank you for the introduction, Dr. Shrestha, once again. We actually created a small video for you guys, so we're just gonna play that back. Feel free to sit back and enjoy the presentation. Then, like Dr. Shrestha said, we'll have questions at the end. If you don't hear the audio within a few seconds, please let me know, stop me, and I'll make sure to get that for you.
Good morning, everyone. Thank you for joining us. My name is Alan Juarez, and I am joined today by my teammates Kyle Michaels, Tomas Diaz, and Leah Harris. We are here to present to you our Senior Design Capstone Project, FSAE Aerodynamics Package and Validation. Formula SAE is an international collegiate competition where students design, build, and race a Formula-style open-wheel race car. The competition is divided into dynamic and static events to showcase the overall potential of the team. Dynamic events include an acceleration run, similar to a drag race, and closed-circuit racing such as autocross, skid pad, and endurance racing. The static events are divided into a design review with industry professionals, as well as the cost analysis and business presentation, where teams must demonstrate their effectiveness in resource management and global development skills. This senior design proposal aims to improve the aerodynamic performance of the 2021 Western Michigan University Formula SAE vehicle. In order to improve dynamic performance at SAE events, a multi-element aerodynamics package comprised of a front wing, rear wing, and undertray was designed. This package was developed with the aid of computational fluid dynamics software to optimize their effect on the aerodynamics of the car. To fully maximize and validate the aerodynamic performance of the package, an electronic data acquisition system was created. Today we will go over the design and development of this aerodynamic package and validation system and its implications on the aerodynamic balance of the car. Lastly, we will cover our results from the simulations performed, as well as recommendations for future development on this topic. The front wing of the BR21 FSAE vehicle is comprised of a multi-element wing and ground effect. The main plane of the front wing contains a structural section modeled after an FX74 mod airfoil spanning 15 inches in length. Beyond 15 inches past the center line of the vehicle, towards the outermost face of the front tires, the main plane splits into two elements, whose total chord length matches the structural section. These elements are placed at a negative angle of attack to maximize its relative location at maximum braking conditions. The front wing also contains a secondary element modeled after an Epler E423 high-lift airfoil. The mounting location and angle relative to ground plane were swept using CFD analysis to determine their optimum location during track conditions. The front wing's secondary purpose is to redirect the incoming free stream air to reduce the amount of drag produced by the vehicle's rotating wheels. In order to achieve this, the end plates, which also serve as a structural component of the front wing, contain a variety of features aimed at redirecting flow outboard of the front tires during track conditions, as you can see by the vertical structures highlighted in this image. For the same purpose, the front wing features underside strakes, which work in conjunction to the end plates to minimize the amount of drag created by the wheels. The geometry of this system allows the front wing to produce a maximum of 115 pounds of downforce at full brake pitch. A minimum drag component of only 8.6 pounds allows the front wing to maintain an aerodynamic efficiency of up to 7.9. The results of these simulations, as well as their sensitivity to various track conditions, is summarized below. Please note all the simulation data presented was performed at 22.23 meters per second, or 50 miles an hour, as mandated by the FSAE competition spec sheets. In order to balance the effects of the added downforce at the front, a multi-element rear wing was designed to the maximum allowed space. The three-element main section is modeled after the S1223 RTL high Reynolds airfoil and optimized for flow during track conditions to maintain balance of the car during maximum braking force. In order to further condition the flow during corner entry, the main plane features a leading edge airflow at the low pressure region of the wing. The end plate geometry is modified to maximize the aerodynamic efficiency of the wing. Horizontal cutouts are located over the main plane to extract air from the high pressure region to be further fed into the low pressure region as charged air via a secondary cutout, maximizing the aerodynamic efficiency. Additionally, the end plates contain a 5 mm vertical gurney to further aid the expansion of the wing, increasing the pressure differential between both sides of the wing.
Next is the undertray. The undertray design is comprised of four main aerodynamic elements: the main plane, venturi tunnels, rear tire deflectors, and M plate with vortex generator. The main plane, centered underneath the vehicle monocoque, is an inverted 2901 airfoil with 70-inch chord length at 1.8 degrees angle of attack. It's designed to account for the geometric constraints of the engine components mounted at the rear of the vehicle, as well as the rear jack bar mandated by the FSAE regulations. The main plane is mounted by venturi tunnels on each side that span 7.5 inches in width. The venturi tunnels are set back 10 inches from the leading edge of the undertray to account for tire rotation, with 3 channels extending 70 inches towards the rear of the car. The third undertray element is the rear tire deflectors, located in the aero development zone between the front and rear tires. This element is designed with 3 Epler E423 high-lift airfoils oriented to redirect the turbulent air over the top of the rear tires, reducing the drag from the wheels and simultaneously providing additional downforce. The fourth and final element of the undertray is the end plate and vortex generator. This final element channels airflow around either side of the rear tire, helping to further reduce the total drag of the vehicle. The integrated foot plate creates a vortical structure sealing the underside of the car to prevent parasitic draw into the undertray, further increasing the aerodynamic efficiency of the component. The proposed undertray design achieves an aerodynamic efficiency of 7.055 at standard conditions, generating 42.4 pounds of downforce. Under half throttle application and 5 degrees yaw, the undertray produces a maximum downforce of 66.1 pounds, improving stability on corner exit. Similarly, at full brake pitch, the downforce increases from standard to 64.1 pounds, increasing handling under extreme braking loads. The proposed aerodynamic designs work in unison to improve the overall vehicle dynamics of the FSAE BR21 race car. At standard conditions, the center of pressure rests at around 17% rearwards of the center of gravity, ensuring the vehicle is dynamically stable during on-track conditions, which allow the driver to extract the maximum performance from the vehicle. This concept has been proven on track by industry professionals in a realm of competitive automotive applications. Shifting the center of pressure rearwards of the center of gravity will counteract the effects of weight transfer during heavy braking conditions. At high braking loads, the center of pressure approximates the center of gravity, allowing the driver to maintain control predictably during corner entry. At partial throttle application, the center of pressure shifts rearwards once again, around 10%, favoring the load on the rear axles, allowing for greater traction at the corner exit. Controlling the center of pressure position allows for predictable handling during weight transfer under braking and cornering conditions. The aerodynamic package designed by our team achieves an aerodynamic efficiency 17.8% greater than its predecessor. Under half brake pitch and 5 degrees of yaw, the improvements to aerodynamic efficiency increase to 40%. Positioning the center of pressure properly during specific on-track conditions can greatly influence the overall vehicle performance. These improvements made by the BR21 aero package correlate to higher lateral loads during cornering, which can result in improved lap times.
Let's now jump into the validation part of our project. Let's start by defining what strain gauges are. Strain gauges are the small instruments or sensors that change their resistance when forces are applied onto them. They're one of the most important and most useful sensors that uses electrical measurements to find mechanical quantities. After the sensors receive their resistance change, that resistance change can be converted into different forces. And for our case, we converted that resistance change into lift and drag forces. For our particular purpose, we use small unidirectional strain load cells. They're located on the top right of the screen. You can see they're very small and very easy to handle. Now, to ensure correct placement of these gauges, we perform a finite element analysis of each of the mounts. We see that we have on the bottom left, we have the front wing mounts. We have in the center, we have the rear wing mounts. And on the bottom right, we have the undertray mounts. In these pictures, we can see the respective strain distribution on each mount. That is the area where the strain gauge should be placed in order to get the most accurate data. Now, as seen in the pictures below, we can see the final placement and location of the strain gauges. We use epoxy resin to attach the gauges into the mounts on the suggested locations. This allows the gauge to stick to the surface without adding any interference to the strain measurements. There were some limitations though. For example, we can see in the bottom left, we have the front wing mounts. The strain gauges were mounted in a different member as the FAA study showed. We did this because we wanted to attach the strain gauges in an area where the environmental factors will affect it, like wind or little rocks hitting the strain gauges. So we put them in this member that is covered by the monocoque. For the case of the undertray that we see in the bottom right, it was a geometrical constraint. It's a very small mount where you can only attach lift measurements. Now, after the strain gauges are fixed into the mounts, it is necessary to calibrate the hardware for data interpretation. The calibration is a process of extreme importance, since this is what will allow the sensor to record and display best accurate values. We can see the calibration curve located on the top right of the slide, where we can see that it's a pretty straight line, and that's exactly what we're looking for. The calibration factor for these sensors was determined by the slope of that trend line associated with the input-output response of the system. In order to get this calibration factor, an assortment of different static loads was used to create a matrix comparing the load applied and the output voltage of the system. This process is repeated in both verticals and horizontal directions to account for lift and drag measurements respectively.
The telemetry side of the validation portion of the project focuses on the wiring, microcontroller, and compiler. The strain gauges are wired together in a full bridge configuration, also known as a Wheatstone bridge. In this configuration, there are 4 active strain gauges per full bridge configuration. Each mount has a set of strain gauges configured to measure lift and a set to measure drag. In order to measure lift, the 4 strain gauges that are configured together need to be in a vertical position. In order to measure drag, the 4 strain gauges that are configured together need to be in a horizontal orientation. The bottom 3 figures are of the front wing mount. The middle photo shows the strain gauges in a vertical position, therefore measuring the strain due to lift on the wing. The thin lines that are present show how the strain gauges are wired together. The picture on the right shows the strain gauges in a horizontal orientation, therefore measuring the strain due to drag on the wing. On this slide, the photos that are to the top right show the rear wing mount. As mentioned previously, the strain gauges are strategically placed so that the strain gauges that are in the vertical position measure the maximum deflection for lift, and the strain gauges that are in the horizontal position measure the maximum drag deflection. The second photo shows how the strain gauges are wired together. The top 4 are wired together to measure lift, and the bottom 4 are wired together to measure drag. To the bottom right of the slide, you will see the undertray mount. The strain gauges are placed in a vertical position, and the second photo shows how they are wired together in order to measure lift on the undertray. From here, the strain gauges are wired to an amplifier. This is so the output values of the strain gauges have a more expanded range so that the data analyzed can be more reliable. The amplifiers are connected to the circuit board, which also has the microcontroller connected to it, and the amplifiers are also connected to the microcontroller itself. The microcontroller is then hooked up to the computer and the corresponding computer program. For example, when we were doing the calibration, we used an Arduino board which talks to the corresponding Arduino program. Or you can also hook up the microcontroller directly to the vehicle's ECU while on-track testing. If the microcontroller is hooked up to a computer program, it will typically allow you to analyze the data either in a table or by a graph, and also depending on the program, the data can be viewed live. The microcontroller contains a compiler, and within the compiler, users can manipulate where the data goes and how it is read based on the code that is written. In this case, if data is sent to the computer, it can be viewed as loads in a table or in a graph, or be viewed live on an LCD screen. However, if the data was sent to the vehicle's ECU, it would be as a 3.3 volt signal.
Using the design techniques mentioned throughout the presentation, our proposed aero package presents a 17% improvement in aerodynamic efficiency over its predecessor, the VR20. Also, the vehicle is able to produce up to 300 pounds of downforce with 40% aero efficiency improvement over the previous models as well. This allows us to maintain a center pressure located 17% rearwards of the center of gravity, providing stability at high speeds and counteracting the effects of weight transfer through critical sectors of the track. Lastly, we were able to create a validation system to quantify the performance of our package with just a minor weight addition. This image shown below is a full render of our proposed aerodynamic package.
Because of the scope and limitations we had over the course of this project, we have some recommendations for the future. First, we would suggest that there would be a validation process of the effects of the high Reynolds flow from the CFD analysis by gathering data through experimental testing of pressure transducers in different areas of the vehicle. Second, we would recommend that there would be use of a multi-axial load cell. The multi-axial load cell would allow for more accurate data to be obtained by reducing the amount of noise from unwanted vibrations and interference due to the bending of the structural members. Lastly, it's recommended to develop the potential of the vehicle's ride by creating a dynamic model of the vehicle in a software that would allow you to take into consideration the weight transfer and aerodynamic load changes depending on the speed and track position.
We would like to extend our immense gratitude to those who helped in the development and execution of this senior design project, to our faculty advisors, Dr. William Liu and Dr. Parvez Maradi, who provided their continued support and insight during these challenging times, to the Formula SAE WMU chapter for being the dedicated sponsors of this proposal. We would also like to give special thanks to David Musa and Peter Tannhauser, who selflessly helped us execute critical sections of this project. Last but not least, we would like to thank our friends and family for being an integral support system throughout the development of this senior design capstone project and our careers. Thank you everyone for joining us in this Senior Design Engineering Conference. We will now open the floor for any questions you may have.
Okay, thank you to the presenters. So please, anybody has the questions, please you can type your question in the chat room, or you can unmute your let's say mic and ask directly, please. Okay, meantime, I just want to ask you a question for all of you guys. So what was the most challenging part at this time doing this project? You're mute. Can you mic, please, mic?
Got it. Thank you.
Yeah.
So I would say we had a lot of ideas of what we were trying to accomplish with both the design and validation portion of it. Unfortunately, due to COVID-19 and the regulations that follow it, we weren't allowed to do a lot of the empirical testing that we had planned out.
Okay, so next one, guys. What is for other guys?
Can you repeat the question?
Yeah, can you just speak individually? What was the most challenging part doing this project at this time individually?
Well, yeah, we worked as Alan was saying with our data acquisition part, strain gauges, all this testing that we needed to do for the validation part of our project. That personally, and I guess for everybody in the group, that was the most challenging part, just because we didn't have access, like physical access to many things. So that was one of the constraints that we presented.
Okay. Kyle?
So we didn't have access to any of the campus facilities that we were hoping to use. Alan already mentioned this, but we had serious hopes of manufacturing small airfoils ourselves to test the pressure difference on the upper and lower side of the member. This would have helped greatly in the development of any of the aero package that we have presented to you guys today. We thought it would have been really great to also use some of the wind tunnel facilities that the campus has at Floyd Hall, but we were unable to secure that due to COVID-19 as well.
Thank you. Leah, you want to add something?
Not really. They all kind of touched on it. Between the COVID-19 regulations, I think that was the hardest thing. And then our original plan was to manufacture, and when we found out that that wasn't going to be able to be a thing, we had to kind of switch the scope of our project on the dot. So that was definitely a wrench that was thrown in, but I think we overcame it well.
Okay, yeah, this was a hard time. I understand that. Even though you guys did a very good job, I'm very happy. I don't know about your faculty mentors, but I'm very happy. And I have one question here in chat. What's the question is elements. So I didn't get it. What is the question? So element, can you see that in the chat? Elements. Can of course elaborate that question a little bit? Whoever typed that, of course.
I think I got the question. It's from Logan Kusharek. He's asking if we gave consideration to active aerodynamic components. So if by active components, it means elements that change angle of attack relative to either track position or speed. We did give consideration to that, and the package will conform of a active rear wing that is driver actuated by a button in the steering wheel. The reason we didn't go through the entire package as an active element is because it changes the predictability of the car, and it's been proven over through empirical data that the driver actuated systems are the ones that prove more reliable and more consistent in terms of driver management.
Okay. Yeah. Hi. Yeah. This was a good effort considering the conditions that we had to go through. Yeah. You guys have done quite a bit of work, except I don't know how much of it is good. The aerodynamics that you did, you used, I believe you used CFD Fluent. Is that right?
No, we actually used Star CCM Plus.
Star CCM, yes, you mentioned that, Star CCM. And it's pretty complicated, what you have in there. Now, how much of that you think is good? Have you even physically evaluated, the results that you get out of your CFD analysis?
Right.
And also you mentioned that the aerodynamic efficiency for your system was 7? What does 7 mean?
So it's the ratio from the coefficient of lift over how much drag it produces. So CL over CD.
CL over CD is 7?
For some components, yes.
Oh, okay. So that's not the aerodynamic, they call that aerodynamic efficiency in the Formula SAE?
Yeah, that's how it's referred to in the literature that goes along with FSAE and SAE publications usually.
Okay, because efficiency usually is less than 100%, and I was wondering how they define that efficiency.
Yeah, so exactly. They define it CL over CD, and since for a lot of our components we have a CL greater than 1, that's where that number higher than 100 comes from.
But that CL, that lift is toward the ground, right?
Correct, yes.
Yeah, okay. Yeah, so were you able to calculate CL over CD for the entire? Now, you guys designed the entire wing system, or you just had the wing system, but the aerodynamics of that, you inputted into CFD?
No, we designed the front wing, rear wing, and undertray. That's what our aero package comprises.
Okay, so you designed the whole thing, but it's not been built to be incorporated into Formula SAE yet, is it?
Not yet.
Ah, okay. All right, thank you. Those were my questions because I wasn't clear whether you guys have. So you were planning to manufacture those components and incorporate it into the actual car and test it.
Correct.
Initially, yeah.
Okay, so that you'll have to make that clear in your report that I hope I haven't read your report that, you know, a lot of this has to be verified,
Right.
right? Okay. That's good. Yeah, that's good. That's good. You guys did a very good job. You learned a lot.
Okay, there's another one question in the chat room, guys. The first question, did you answer the second question? There are limitations in the regulation regarding the active elements in SAE, Formula SAE. Do you know?
I think that was Kyle in the question in the chat.
Yeah.
Okay. So
Yeah,
the
so
next
the-
question now. Okay, go ahead.
I was just going to say the only limitations that are there are the drag reduction system, which we talked briefly about, is the only allowed active aero element as far as I know. There are regulations that bar any unnecessary movement from other aero elements in the car.
Thank you. And there's one more question here from Professor Rowe. Can you show the CFD analysis result again?
Yeah. Do you have any specific part of the CFD analysis that you would like us to show? We have a front wing, rear wing, and under tray simulations as well as full car. Let me share my screen here. Okay.
So complete figures. So can you just share that once again?
Yeah. Just 1 second. So this is, for example, when we were speaking about the front wing specifically, but you can see it's partly the monocoque chassis and the front wheel as well. If you would like me to go back to the video, let me know and we can.
No, okay, we have no time for that anymore. Please, if you have, you can contact Dr. Rowe separately after this. And presenter, thank you very much for your presentation. Appreciate it. And of course, we'll start the next presentation at 10 a.m. after 3 minutes. So we'll conclude this presentation to, here, and I stop recording for now. Stop. Stop recording.